Section 7.2, we're going to do calculus of parametric curves. Now that we have learned how to do parametric curves, the next step, we're going to figure out what's the derivative of the curve that we're talking about. So to do the derivative, let's go to the next page, where theorem 7.1, where we have some kind of a parametric equation, okay? And then suppose that we assume that various things exist and stuff, and of course we do have to exist that x prime of t is not 0. The reasons is because of the way the definition works. So here's the definition. The derivative dy by dx is given by dy by dt over dx by dt, and which is y prime of t over x prime of t, which at this point you see why the the x prime of t can't be 0, because then you'll be dividing by 0, and that's not acceptable. Now let's look at the short proof. Okay, we are going to prove it by the chain rule. So let's say that we will have the parametric equation. Let me write this stuff down. So we have the parametric equations, and we are going to assume that there's a way to plug this thing in there or that thing in this, so that you end up with some kind of a function that y equals to f of x, by eliminating t, as we have done in the previous section. Or put it another way, is that y of t equals to f of x of t. So this thing will work out like that. Now we will do the chain rule, which states that y prime of t equals to big F prime of x of t, and then take the derivative of the inside, which gives you x prime of t, and then so then you get, dividing this thing out, then you get big F prime of x of t equals to y prime of t divided by x prime of t. And then at this point, then what is this thing? Well, this thing is the same as dy by dx, okay? Because y is big F of x. Therefore, dy by dx is f prime of x of t, and therefore that's your proof. Short and sweet. Anyway, so that's that. Now that we have the proof, we'll sort of ignore it, and from now on we're going to follow this formula. So the derivative of dy by dx of your parametric equation is y prime of t over x prime of t, and that's the formula you're going to follow when you are told to find the derivative. So first example, 7.4, which is on page 627. Let's find some derivatives. What are we doing here? Okay, you're supposed to calculate dy by dx, and you have a, b, c, 3 things to calculate. So that's what you're gonna do. Okay, go ahead and well, you just follow the rules and take the derivative, and out comes the solution. Yeah, that's all you need to do. So please do example, what is this again? 7.4 as part of your homework. Actually, we could have done this in Calculus 1, because this is all you do in Calculus 1. Take the derivative, and stuff falls out. But anyway, and then the next problem, the next example, same thing, finding a tangent line, just like you did in Calculus 1. So go ahead and do example 7.5 as part of your homework as well. Yeah, you take the derivative, and you do the point slope formula, and out pops the tangent line like you're supposed to. Now the next thing we're gonna think, well, what about the second derivative? That is d squared y by dx squared. How would that come out? So let's consider that, okay? And we're not gonna care anything above that, because is not that interesting. So d squared y by dx squared, the second derivative, is of course given by the derivative d by dx of the first derivative, which is dy by dx. And to come up with the formula for the parametric equation, what we're going to do is plug something right in there. That is, we have dy by dx of the parametric equation as given over here. I'll write it down again. Okay, it's this thing, all right, which is dy by dt over dx by dt. And what we're gonna do is plug the y in here. So that is equal to on both sides. So then we'll turn the y, let y equal to, replace y with dy by dx on both sides. So replace y with dy by dx. Then we have on this side, what is y? Y would be dy by, we plug the dy by dx in there. Yeah, okay. Let me see. Now let me write that down first. So what we're doing here is replace y with dy by dx. So what we have, see, y got replaced with dy by dx. And then this y also get replaced with dy by dx. So we have d by dt on top of dy by dx over dx by dt. So that's so far so good. And this is the second derivative, okay? And so what you're gonna do to calculate a second derivative is you're gonna do this part if this thing is in terms of t. Otherwise, you can't take the derivative. But if you can figure this thing out in terms of t, then everything works out okay. So let's look at, as an example, let's look at example 7.6, where you have some kind of a parametric function, and then you can, it happens that you figured out what dy by dx in terms of t is. Okay, it calculates to be 1 over t, and at that point, then you just plug it into this formula right here. You take the derivative again, and over dx by dt, and that's your answer. So please do example 7.6 as part of your homework. And we'll move right along to the next thing, which is integration. Now to integration involving parametric equations are basically the same, well, are the same as integration of some regular function that we have done. What we're gonna do is use the Riemann sum and then use the mean value theorem. The mean value theorem, which will give us the formula, the formula for the integral. Let's see, I will clean the board. So to do integration, let's look at page 632, where we have we're going to draw the exact same thing we did in Calculus 1. We're going to draw a bunch of rectangles and calculate the Riemann sum. So the rectangles are given by the height of this thing is x. This is y, okay? The y value will be equal to y of x of ti with a bar on top. The bar means is the bar just means the ti is somewhere in here. We don't really care where, so we put a bar on top. It's somewhere between t0 and t1, or t1 and t2 for each rectangle. So that's just for one of them. And anyway, so having said that, each area for all of these things, here's a sample, okay, area of I. So AI will be equal to length times width, okay? The length is y of xi of t, xti. X doesn't have index, just t. Let's write this better. Okay, x and ti, where ti is, we'll put a bar on top. Ti is anywhere within the rectangle we're talking about, so one of these. And then keep going. So that's the length, okay? The width is then x of ti minus x of ti minus 1. The minus 1 is incrementing I. Okay, there are a lot of symbols. This is an I minus 1. Now there are a lot of symbols here, but do not let that blow you over. This is the exact same thing we've been doing. We're doing length times width. Okay, it's just there are more symbols now, but nothing's different or more difficult. So then of course the entire sum is when you add this whole thing up. Okay, so the whole sum, the whole area then is sum of ai when I goes from 1 to n. I equals to 1 to n. That would be your entire area. But now we're going to, I guess the book doesn't want to bother with mean value theorem. We're just going to pull a quick trick. So then we'll rewrite this sum as this thing. We're going to write this thing out, okay? But we're going to do something different. Is so it equals to y of x of ti, t bar I. This whole thing is just one number. This is the height of your sample strip, rectangular strip. And so that's the height. And then I'll copy this thing down again. So we have x ti. Again, that's just one number, right? Or one variable. Anyway, so, well, it's not one variable, but you get my idea. It's one number. X ti minus 1. All right. And then I've copied this down. What we're going to do is pull this trick. We're going to divide it by ti minus 1. And then multiply it by the exact same number, minus ti minus 1. If we multiply and divide by the same number, we haven't changed anything. Okay, ti minus 1. But what happens, the reason we're doing this is that this thing right here, as n goes to infinity and everything gets smaller and smaller, this is the definition of x prime of t. This thing right here. So let me write this a little clearer. So just this part is the same as x prime of t. X prime of t what? Anyway, it's the derivative. It approaches x prime of something. And then well, for t that's within here. Okay, from ti to ti minus 1. Or maybe I should write this thing down, t bar. So anyway, yeah. Anyway, this approaches it, and then this part, of course, approaches delta x. Delta t. So then now that you realize that, then this particular equation then approaches, so the area, which is the limit as n approach infinity of an, is the same as the integral. Okay, we're adding from t goes from a to b of the first part is y of t. The second part is x prime of t, whereas the ti bar just goes to, well, t at that point, because everything's going to infinity. And then the third part is dt. So that's how the formula is derived. And yeah, you can see that that's almost identical to how we do any other integral. So having said that, we're ready to use this thing for something. So the area under a parametric curve is given by, on the next page. The area is from a to b. If you have x of t and y of t goes from a to b, and t has to be non-self intersecting. That matters because if it goes around and around, you're going to crank out too many areas. Anyway, the point is the graph can't cross itself. Okay, so as long as that's true, we have the area as given is integral from a to b yt x prime of t dt. So that would be our nice little area. Now, having said that, now that part is, now that we have proved it, we are going to use the formula and not worry about the proof anymore. Okay, now to use the formula, of course, you just plug stuff in, follow the formula, and do integration. Well, first you have to take the derivative of x of t, and then integrate the stuff yt x prime of t, and then you evaluate the value and hope that something falls out correctly. And that's example 7.7. Please do example 7.7 as part of your homework. Next, let's look at the arc length on page 634. Now, the arc length is calculated exactly the same way as is done in Calculus 1, but we'll repeat this process. There's a slight difference because things are done parametrically, but the principle stands the same. And the principle, of course, is the Pythagoras theorem, where a squared plus b squared equal to c. So we have a squared here, and then there's a, b, and c, and then we have the good old principle. Well, anyway, so then what that happens is that you have a curve, right? And then we're going to do a small part of it so that it looks almost straight. And then we'll calculate the small part. And what is that? Well, that's the difference in x. So we will calculate it as same as here. So the x difference is x. Let's see, is x. Well, this time your book wants to call it k, even though we call it I before. So we'll call it k. K is fine. So we'll have x of t of k, okay, minus x of t of k minus 1. So this thing is being squared. That's the x squared. Okay, that's the bottom squared. And then added with the same thing with y. Added with y squared. Exact same thing. Y t of k minus y t of k minus 1. This is also squared. Okay, that's a squared plus b squared for this tiny little bit. Okay, this is the x difference, the y difference, and you square it, and then you take the square root of this stuff, and that equals to the hypotenuse length, right? That's c squared. So you have to take the square root, and that's just one small part of it. And then then you add up the entire deal. It will become it will approximate the arc length. At this point, however, we are going to apply the mean value theorem, where this difference right here, by the mean value theorem, the difference that is x of t minus x of tk minus x of tk minus 1 is, by the mean value theorem, equal to x of prime. That is the derivative of t at some point. Okay, we'll call it, I don't even know, what is that thing called? I don't care. So that is some point of t between k and k minus 1 by the mean value theorem. It equals to the difference equals to the derivative times the t difference. So tk minus tk minus 1. Now, if you don't remember the mean value theorem, please look it up in Calculus 1. But the point is, the difference of a function is equal to the derivative of the function of some point, okay, in times the difference of the domain, well, whatever this is. It's the difference, okay? Trust me, that's the mean value theorem. So we replace that thing with this thing right here. So that's squared. And then the y, we do the same thing. And what is this thing? This thing is the same as delta t. And then when we sum this whole thing up, it ends up being, so we do the same thing with y. I'm going to skip the writing here because I ran out of space, plus I'm lazy. I don't want to bother. So then by the time you're done with it, then you let n go to infinity. Then you clean it up. So then you have the answer. What's the answer? Is on the next page. As n goes to infinity, this is going to be x primed. Okay, and of t squared. And then plus y prime of t, also squared, and then take the square root, and you factor out the delta t, and the delta t becomes your dt. And you integrate it from wherever you're supposed to integrate, t from a to b, and that is the formula for the arc length. Now, isn't that neat? So the which, as you can see, looks almost identical to the original formula for arc length, if you are to look it up. And it basically is the Pythagoras theorem all added up, okay? So that the same deal. So having said that, yeah, well, and actually you can derive this thing and go back to the original formula. Here's the original formula for the arc length when it's not parametric, and then you can go from one to the other by some manipulation, but we're gonna skip that because that's just a lot of grunt work. But feel free to do that if that interests you. Anyway, let's get to the homework. I mean the example 7.8. So example 7.8, you are gonna, well, there's not much to talk about except that you're gonna follow that exact formula to come up with something. The length of half a circle, which is something we already know, but you're going to use this formula to do it to test the formula to see if it works. Okay, you better not come up with a different formula for the diameter than what we already know. And it does come up with the same answer, so that's reassuring. So please do example 7.8 as part of your homework. Next, on page 636, let's look at the baseball problem. Now, what about the baseball problem? Well, the baseball problem requires you to calculate the arc length, which is the path of the baseball, which is now, as you can see the problem at the bottom of the page, 636, we have x of t is 3t squared, y of t is 2t cubed, and what? No, that's something else, sorry. Is actually x of t is 140t, y of t is, t squared. It doesn't look so bad. However, but as you can imagine, arc length problems get messy a lot, really fast. And in this case, it looks even messier than you would imagine. Sorry, it looks, yeah, it looks, turn to the next page and you realize that this thing looks a lot worse than you might imagine it. So please do this problem as part of your homework. Now the problem itself, the integration is quite straightforward. There is a formula from the back of the book, page 700. Okay, so the integration is already done. So what's the rest of this stuff? The rest of this actually is just plugging in the numbers, and the numbers get to be huge. Please look at the page and see all the numbers. But I want you to do this anyway because normally I wouldn't ask you to do a ton of grunt work because I think grunt work is just annoying. But once in a while, we should do some grunt work, even though we're studying math as a hobby, just to show that we can. Okay, and this is an excellent opportunity to do a problem that is extremely messy. It's important that you do this once in a while so that even though we don't normally get our hands dirty and do this, we know how to do it if we have to. Okay, and so this is an excellent opportunity for that. So please stare all these numbers and try to make sense out of it. And remember, messy does not equal difficult. Messy just means there's you have to write a lot of stuff. But the principle is very simple. Or straightforward because, the integration is already done. You just have to plug the numbers in. The only problem is you have a ton of stuff to plug in, see? And but eventually, what that means is if you mess up somewhere, you're going to be completely dead. So please do this by yourself. And then if you do mess up, do it again. Okay, you need to get this to come out because to prove to yourself that you can handle not just clean problems where things are all neat and beautiful, but even if it's messy, you still know how to do it because messy and clean are not different. And not quite the same as messy and difficult. And then the next step is, you have to calculate the speed of the baseball, which is fine. You just take the derivative. In this case, you don't even have to take the derivative. It's just is just well, is whatever it is. And then the next page, we have to calculate some numbers. Okay, now here's another thing I want you to do. Now if you keep going, they for some reason want to know what s of 1/3 is. Now the s of 1/3 is a whole pile of numbers multiplied together. Now this is just algebra. This isn't even calculus. However, I've heard engineering professors complain that the calculus students can't use the calculator. Why? Because, well, for this type of thing, when the numbers get complicated, the calculus students, I don't know, got lost or something, which is not acceptable. Okay, now you need to know how to use the calculator to, even for a problem that looks like a headache, like this thing here. So please use the calculator, your calculator, whichever one it is, in your cell phone, the TI-84 computer, whatever. You need to type it in correctly so that the right answer come out. Okay, don't come out of my class and you go to engineering or something and somebody complain about you to me that you don't know how to use a calculator. Goodness. Well, figure it out. I mean, I don't know, if you can't get it to come out, look at the manual. I don't know, do something. Okay, you have to get the calculator to work. That is, you need to be absolutely sure that you know how to punch the buttons on your calculator correctly. Okay, so that's that. So there's a messy but easy problem. Okay, and and so please do that the baseball problem on page 636, and then we'll go to the next one. The next I think we have to do is calculating the area. Okay, and then that's when it quit. I guess it doesn't care about volume or something. What it was spin stuff. Does it say volume? No, we stop at area because the area of surface area is to the parametric curve. That is, if you spin some curve around, okay, around some axis, in this case the x-axis, is spin it around, and then you can calculate the surface area. Here's the original formula for when we're not parametric, right? And then you look down a little bit. The new formula is not that different. You just need a t in there. But in this case, the book isn't even going to bother proving this to you because it's probably tired. And so we're also going to skip the proof because the proof is almost identical. It's the same principle. You just, I don't know, use the mean value theorem or something and everything falls out. Except that you do have to write a lot of symbols and not get blown away by too many symbols. Anyway, so example 7.9, finding the surface area. What are you looking for? Oh, the surface area of some sphere. You already know what the answer is, but this is to test the formula to see if it works. It better not come up with the wrong answer. And luckily, it does come up with the right answer. So please do example, what is that? 7.9 as part of your homework. So for homework of this section, please do problems 65, 67, 73, 77, 81, 85, 89, 95, 99, 103, 107, 109, 115, and 123. And when you're done, I want to talk about it. Now that you're done with the homework, I want to talk about some of them. First one is 107. The problem 107 is describing some teardrop. So please plot this thing out on the calculator. You don't have to, but it's cute. You know, you watch this perfect teardrop being plotted, especially if you let A equal to 1 and then B equal to 5. Then otherwise the teardrop looks too fat. But if you get B equal to 5, then it looks perfect. You know, exactly like a teardrop should look. So having had enough fun to look at the teardrop, then we're going to calculate, what are we doing? The area? Yeah. So to calculate the area, you write down the formula of the area. You take the derivative of x, and then you come up with some integration that looks a bit hard, but not impossible. So here's what I did, right? So here's the problem. I wrote down the formula. I took you're supposed to take x prime of t, which I did. It's right here. And then you have the formula, and the formula has some variables in there, minus a to ab. Now it's a good idea to take it out, okay, put it on the other side. So a over minus 2ab equal to this stuff. Now once you have taken it out, and in fact I have it written down in two integrations because then it's much easier, right? The sine squared has a standard formula, which is rule 18 on page 700, the integral tables. And then sine t cosine 2t is rule 36. And if you follow the rules and then evaluate the from 0 to pi, etc., and you get something like this. Or you can just combine this as one integral and type it into the definite integral calculator, and that'll give you the same answer. It just equals to pi, because once you take out the variables, then you can type it into the calculator. So so you have this, it equals to pi, and then and that's a over minus 2ab. So then the whole area is 2ab pi. There's a negative sign there, but we're going to ignore it because we don't care if the area is negative. And that is actually the right answer at the back of the book as well. So that makes for a pretty neat problem. And then if you graph it, then you can see the beautiful teardrop, which makes doing this problem worth it, to see such a nice teardrop. Yeah, without us having to draw it, see? Because I'm not good at drawing, so having math draw a teardrop for you is pretty neat. Okay, next I want to talk about 109, problem 109. Yeah, so this time we're doing arc length. Arc length, so you follow the arc length formula. The arc length formula says something about x prime squared, then y prime plus y prime squared, square root, and then take the integral. So you do exactly that. You can factor out the t, and that turns out to be an easy integral to factor. Now you can either do the factor yourself, do the integral yourself, which is what I did here, being that it's pretty easy. Or you can just plug it into the definite integral calculator and come up with the same thing. See, here it is. And that is the correct answer. Not much to it. The same as problem 123. What is it? I think that's a surface area. So I wrote down the surface area formula, did all the proper derivatives. Here's x and y. X and y are, very simple formula, simple things. So that makes the derivatives better. And then I end up with, it just happens to be the exact same integral. See? It's t times 1 plus t squared square root. But by now I'm tired. Okay, so I just plugged it into the integral calculator, and out comes that thing, which is identical to the back of the book, and answer at the back of the book, and that's good enough for me. And that marks the end of this section.